You think you understand electricity? Get ready, because I'm about to reveal a truth that might astound you. The interesting and somewhat ironic thing is, you use electricity every day, everywhere. You flip a light switch, charge your smartphone, or heat up a meal in the microwave. But if I were to ask you, what is electricity really? Chances are your answer would be not entirely correct. Don't blame yourself, because even many electrical engineers have misconceptions about what actually happens when they flip a switch. And that's the beauty, the allure of physics, when you discover that things aren't as simple as you always thought. In fact, what you were taught might not have been accurate at all. When I was a kid, I was taught that electricity was like water flowing rapidly through a pipe. They said that electrons would flow from the battery, through the wire, to the light bulb, and light it up. Sounds simple, right? A beautiful, neat, easy to visualize image. But there's a big problem. It's fundamentally wrong in crucial ways. First, I want to ask you a question. How fast do you think electrons move in a wire? If you compare electricity to water in a pipe, you'd probably think they must move very quickly. After all, when you flip a switch, the light bulb turns on instantly. So the electrons must be zipping from the switch to the light bulb very fast, right? Want to know the shocking truth? Electrons in a normal copper wire move at a speed of only about, listen carefully, 1 millimeter per second. That's right, you heard me correctly. Just 1 millimeter per second. Wait a minute, let's think about that. If electrons only crawl at 1 millimeter per second, how does a light bulb 3 meters away light up instantly the moment I press the switch? Sounds absurd, doesn't it? And that's the moment you realize that what you thought you knew inside out, you didn't really understand at all. That's why I'm so fascinated by physics. The real secret about electricity is right here. What's actually happening, and get ready, because it will completely change the way you see everything. Electricity is not the flow of electrons. Instead, electricity is, in fact, an electromagnetic field propagating through space. Let's explore an intriguing mystery about how energy truly works. To start, imagine you have a long pipe packed tightly with marbles. If I push one marble in at one end, what do you think will happen? The marble at the other end will pop out almost instantly, right? It's not that the marble I pushed traveled all the way through the pipe. That would take time. Instead, it transferred its force to the next marble, which then pushed the next one, creating an instantaneous chain reaction. Now, this might seem similar to how electrons work, but that's only a tiny piece of the puzzle. The real story is far more magical and beautiful. When I connect a battery to a circuit, I'm not simply turning on the current. What I'm actually doing is establishing an electric field, an invisible wave that propagates through the space around the wire at an astonishing speed, almost the speed of light. And it's this invisible electric field, not the slow-moving electrons, that is the true hero transmitting the energy. Electrons aren't the messengers carrying energy. They're more like diligent workers in a factory, merely rearranging tiny parts. But the core action, the actual transmission of energy, happens right within the electric field surrounding them. To truly change the way you perceive this, I'm going to present another thought experiment, an example that will clarify all of this. This is a thought experiment I particularly love, often used to break students' deeply ingrained preconceptions. Imagine I have two enormous parallel metal plates, each as wide as a football field, and they are placed just 1 meter apart. I'm going to connect a battery between these two plates. What will happen? Well, the battery will immediately create a significant potential difference between the two plates. Electrons will accumulate on one plate, making it negatively charged, while the other plate will have a deficit of electrons, becoming positively charged. And this difference will create a uniform, strong electric field between the two plates. Now here's the truly interesting question. If I place a tiny test charge, say a single electron, anywhere between these two plates, will this electron feel a force? Absolutely, it will feel a force from the electric field. But here's the fascinating crux. Where does that force come from? Is it from the billions of electrons on those metal plates? Not at all. It actually comes from the electric field itself, which permeates that space. The electric field isn't an abstract concept. It's a real, tangible entity, as real as the metal plates themselves, and it carries both energy and momentum. When we delve into Maxwell's equations, and yes, I absolutely must talk about them because they are too beautiful to ignore, we will discover an extraordinary truth. Energy flows continuously, following the direction of the vector product between the electric and magnetic fields. Let's explore a crucial concept, the Poynting vector. It's the key to visualizing the flow of electromagnetic energy. And here's what might truly surprise you. This energy flow, contrary to common belief, doesn't travel inside the wire. Instead, it courses through the space surrounding the wire. That's right, you heard me correctly. Energy doesn't move inside the conductor. In fact, most of the energy in an electrical circuit doesn't pass through the wire itself. Instead, it glides through the space enveloping the conductor. I know this might sound absurd, even like a joke, but trust me, it's absolutely accurate, and we can rigorously prove it using Maxwell's magnificent equations. As current flows through the wire, an electric field forms along it due to the potential difference. Simultaneously, a magnetic field also encircles the wire, a direct consequence of the flowing current. The Poynting vector, which indicates the direction of energy movement, is always perpendicular to both the electric and magnetic fields. This confirms, once again, energy truly flows in the space surrounding the conductor, rather than threading its way inside it. Of course, the electrons inside the wire aren't idle. They create the current, and this current, in turn, generates the necessary magnetic field. However, the actual energy, the energy that lights your bulb or powers your computer, is gliding through the electromagnetic field, right in the surrounding space. Picture it this way. The wire acts more like a guide for the electromagnetic field rather than the primary carrier of energy itself. So if you're confused and asking yourself, wait, if energy doesn't travel in the wire, then why do we need wires? You've hit upon an excellent question. If energy truly glides through the surrounding space, then what is the role of the conductor? You've posed a profoundly insightful and precise question. This is precisely the kind of question that opens the door to truly understanding the nature of physics. The answer lies in this. The conductor performs two extremely crucial tasks. Firstly, the wire acts as a guide for the electromagnetic field, while also providing a low-resistance path for electrons to move easily. It is the movement of these electrons that is the key factor in generating the necessary magnetic fields. Without the flow of electrons in the conductor, we wouldn't be able to establish the correct electromagnetic fields. Secondly, the wire completes the circuit. This is paramount to ensuring a continuous and uninterrupted flow of energy. For current to truly flow, I need a closed path, a journey that electric charges can complete, returning to their starting point. However, here's a crucial point that many often misunderstand. Just because we need wires doesn't mean the energy is flowing through them. In reality, wires are merely guides to establish and sustain electromagnetic fields. And it's these invisible fields, not the wires themselves, that are the true carriers of energy. Let's pull back the curtain on the secret behind the electric switch. I remember, as a curious boy, a question often puzzled me. You just need a light touch on the switch and voila, the light bulb illuminates almost instantly. But hold on a second. We just learned that electrons only crawl at a mere millimeter per second. So how can a signal travel so fast, almost instantaneously? The secret lies here. When you close the switch, what you're actually doing is not pushing electrons, but creating a disturbance, an instantaneous change in the electric field right at that point. And this electric field disturbance, like a ripple, begins to propagate throughout space. It's exactly like an electromagnetic wave traveling at the speed of light, Well, more precisely, at a speed dependent on the medium, but usually a very significant fraction of the speed of light. So when I flip the switch, the electric field right here changes, and that change propagates extremely quickly, encompassing the entire circuit. The electrons in the light bulb react to this field change almost instantly, not because the electrons from the switch have traveled there, but because the electric field itself has shifted and changed. Imagine a wave of people in a stadium. Each person representing an electron only shifts up and down slightly in place, but the wave itself, the electric field, sweeps rapidly across the stands. So, what is the true culprit behind electrical resistance? Now, I want to delve deeper with you into a concept that most people probably think they already understand: electrical resistance. You might have heard that electrical resistance is just like friction in a pipe, right? That electrons constantly collide with atoms, and that's the cause of resistance. Well, the answer is partly true, but not the whole story. You see, if resistance were merely friction, meaning electrons just crash into atoms and bounce back, then at higher temperatures, when atoms vibrate more vigorously, resistance should significantly increase. And indeed, that's exactly what we observe in metals. But hold on. In the world of metals, electrons are not like tiny marbles just randomly colliding with atoms. Have you ever wondered what really happens inside an electrical wire? Let's explore. The electrons in metals are in fact quantum waves, mysteriously gliding through the atomic lattice. And here's what truly amazes me. If that crystal lattice were absolutely perfect, if every atom were perfectly aligned precisely in its correct position, then you know what? There would be no electrical resistance at all. Those electron waves would glide straight through, encountering no obstacles or interactions whatsoever. So the resistance we observe, it arises precisely because the crystal lattice isn't as perfect as we imagine. It contains strange impurities, tiny defects, and even thermal vibrations, which we call phonons, that disrupt that perfect arrangement. It's these imperfections that scatter, that deflect the electron waves, and that, right there, is the origin of electrical resistance. So I want you to imagine this. Resistance isn't like friction. It's more like a sound wave trying to weave its way through a chaotic environment. These irregularities scatter the waves, and this also helps us understand why superconductors, materials with zero resistance, are so miraculous. In a superconductor, electrons pair up. We call them Cooper pairs, and they behave collectively, allowing them to glide through the lattice without being scattered at all. It's as if those imperfections suddenly become blind, no longer able to see the electrons. And having discussed the quantum nature of electric current, of these quantum waves, I want to tell you something even stranger. Electric current, at its deepest essence, is an entirely quantum phenomenon. When an electron moves through a wire, don't think of it as a tiny particle traveling in a straight line. No, it's a probability wave spreading out across space. And when I say there's an electron current, what I really mean is there's a net flow of these strange probability waves themselves. But here's what truly fascinates me. Those individual electrons aren't independent. They're entangled with each other. Quantically, they are tightly entangled with the entire system. You can't isolate a single electron and point to it, saying, this is the one carrying the energy. All electrons in a conductor are quantum mechanically correlated with each other. And furthermore, thanks to the Pauli exclusion principle, a principle stating that no two electrons can ever occupy the same quantum state. The electrons in metals form a special structure that we call a Fermi gas. Imagine this. Even at absolute zero, electrons are in constant motion, carrying an incredible amount of energy and zipping around at astonishing speeds. The Fermi velocity, a truly astounding figure, often reaches a staggering 1 million meters per second. Yet, here's the strange part. We've also claimed that electrons only move a mere millimeter per second. So what's the truth? The crux of the matter lies here. We're dealing with two entirely different concepts of velocity. Drift velocity, which is what we typically measure when talking about electric current, is actually just a mere millimeter per second, or even slower. However, individual electrons are hurtling around at incredible speeds, many times faster, and they're moving chaotically in all directions. Drift velocity is simply a very small overall displacement, a gentle nudge in a specific direction, superimposed on their chaotic and extremely fast dance. Imagine a swarm of bees buzzing frantically, each bee darting around at breakneck speed in every direction. Yet viewed as a whole, the entire swarm is slowly moving in one general direction. And here's something even more fascinating: the real secret hidden inside every battery. Now let's delve into batteries, because there's another common misconception that many people still hold. Many mistakenly believe that batteries store electrical energy or contain electrons. No, that's absolutely not what batteries do. In reality, a battery is a reservoir of chemical energy. When you connect a battery to a circuit, the chemical reactions happening inside it generate an electric field. This electric field's job is to stimulate and push the electrons already present in the wire to start moving. Batteries don't pump extra electrons into the wire. Remember, the electrons are already there. They're always present. A copper wire, for instance, contains countless free electrons at an astonishing density of about 10 to the 29 electrons per cubic meter. So the battery's true function is to provide the necessary energy to propel these pre-existing electrons into motion. Imagine this. You're in a room packed with people, and suddenly someone from the next room shouts, "Free food!" They didn't bring more people into the room. Instead, they just got the people who were already there to start moving. And here's another interesting fact you should know. When a battery dies, it's not because it has run out of electrons, because the chemical reactions producing the electric field have come to an end. All chemical potential to convert into electrical energy is gone. A classic yet challenging question: why are birds safe when perching on high voltage power lines? This is a paradox that makes many wonder. How can a tiny creature perch freely on high voltage lines without any harm? The common explanation is birds only touch one wire, not two, so there's no voltage difference. However, that's only one piece of the puzzle. The core truth lies here. Voltage itself is not the killer. The deadly agent is current, especially when it flows through the heart or other vital organs of the body. When a bird perches on a wire, it's true that the wire carries enormous voltage, potentially tens of thousands of volts. However, a bird's body has a certain resistance, and more importantly, because both feet are on the same low-resistance conductor, according to Ohm's law, the voltage difference between its 2 feet is extremely small. With such a tiny voltage difference between its 2 feet, the current I flowing through the bird's body will be extremely weak, even if its resistance R isn't too high. However, if the bird accidentally touches 2 different wires, or one wire and the ground simultaneously, then a huge voltage difference will appear, causing an extremely strong current to flow through its body, and that would be the end. The lesson learned is, voltage itself is not the threat. Real danger arises when voltage finds a path for current to flow. And this brings us back to a fundamental idea. Electricity is essentially the movement of energy within fields, far beyond the simple concepts of voltage or individual electrons. Now we turn to a classic confrontation: alternating current AC versus direct current DC, a battle of energy flows. This historical account will reveal more misconceptions about electricity. In the late 19th century, 2 great minds, Thomas Edison and Nikola Tesla, became embroiled in a fierce debate that went down in history. At the heart of the dispute was, should the power distribution system be based on direct current DC or alternating current AC? Edison staunchly defended DC, while Tesla was the pioneer for AC. Edison did not hesitate to stage numerous gruesome public demonstrations to prove the dangers of AC, even electrocuting an elephant, an incredibly cruel act. Yet, in the end, AC achieved a resounding victory, and today, almost the entire global power grid operates on alternating current. AC didn't win because it was inherently superior to DC, but rather due to its outstanding practical technical advantages. With AC, the use of transformers allows us to easily adjust voltage between high and low levels, a crucial advantage. To transmit electricity over long distances, the secret lies in using extremely high voltage. This is because energy loss in transmission lines always follows the law P equals I squared R, meaning it increases with the square of the current. The amazing thing is, by simply doubling the voltage, we can halve the current, because the transmitted power, P equals VI, remains constant. Therefore, halving the current allows us to reduce energy losses to just 1/4. But here's the crucial point. Thanks to advanced power electronics technology, we can now convert direct current DC and various voltage levels with incredible efficiency. And surprisingly, in some specific applications especially, in fact, for long-distance power transmission, direct current DC significantly outperforms alternating current AC, which is why we are witnessing a strong resurgence of high-voltage DC transmission. It's important to understand that there's no golden answer that applies to all situations. Every choice must be based on the specific application context and current technology. Physics defines the limits of what's possible, while engineering is the art of making those possibilities a reality. Let's return to a crucial, often misunderstood topic, the true speed of electricity. On one hand, we know electrons drift very slowly, only a few millimeters per second. On the other hand, when a switch is flipped, the light turns on almost instantly. Is there a contradiction here? So how do we resolve this paradox? The key is to understand that multiple types of speeds coexist within an electrical circuit. First, we have the electron drift velocity. This is the average speed at which electrons slowly move through a conductor, merely a few millimeters per second. Next is the Fermi velocity. This is the astonishing speed at which individual electrons move due to their intrinsic quantum energy, reaching millions of meters per second. However, because this velocity is entirely random in all directions, it does not contribute to the overall current we observe. Finally, and most importantly, there's the signal propagation speed. This is the velocity at which changes in the electric field travel along the conductor, often a significant fraction of the speed of light. To visualize, it can be as fast as half the speed of light in a vacuum. Therefore, it is this third speed, the signal propagation speed, that is the key factor determining how quickly electricity appears to flow. The light turns on instantly when the switch is pressed, and that's a truly astonishing phenomenon once we understand its nature. This speed is not constant. It is also influenced by the characteristics of the conductor itself and its surrounding environment, such as in a coaxial cable. Imagine this. The speed at which an electrical signal travels through a cable isn't random. It's shaped by the insulating material between the conductor core and its sheath, specifically its dielectric constant and magnetic permeability. And here's the fascinating part. In the world of high-speed communication, how fast a signal travels is absolutely critical, especially when you're building the electronic brains for high-performance computers. You even have to meticulously calculate every millimeter of cable length, because signals can't instantly appear at the other end. They need time to traverse that distance. Let's take a concrete example. At a frequency of 1 gigahertz, the signal's wavelength is a mere 30 centimeters in a vacuum. That's why even a few centimeters difference in cable length can create synchronization nightmares, throwing the entire system out of sync. Unraveling the mystery of inductance. Now I'm going to reveal an aspect that makes electricity not just a simple flow, but something far stranger and more complex than we usually imagine. Inductance, what is its essence? Simply put, whenever an electric current flows through a conductor, it automatically generates a magnetic field around it. You probably already know this. But here's the crucial, truly fascinating point. If you try to change the strength of that current, the magnetic field around it will instantly change as well. And according to Faraday's great law, a changing magnetic field will generate an electric field. The remarkable thing is that this induced electric field tends to oppose or resist the very change in the original current. Just imagine an electrical circuit having its own inertia. You can't force the current to change abruptly because the magnetic field always tries to resist any such fluctuation. And that is the essence of inductance. This is also one of the core reasons why alternating current AC circuits operate completely differently from direct current DC circuits. In the world of direct current DC, everything is simple. The current always maintains a constant value. Once the circuit reaches a steady state, there's no longer any variation in the magnetic field, and therefore inductance plays almost no significant role. Conversely, with alternating current AC, the flow constantly reverses and changes, making inductance an extremely crucial factor. In fact, it's the complex interaction between inductance and capacitance, another property arising from changing electric fields, that opened the door for radio waves, microwaves, and essentially the entire foundation of modern wireless communication technology we enjoy today. And all of this leads to a core truth. Electric fields and magnetic fields are inseparable. They are intimately linked, like a shadow to its object. You can't have one without the other. When things are in flux, they are simply two sides of the same grand coin, the electromagnetic field. Maxwell's equations, the portrait of truth. All right, I can't resist mentioning Maxwell's equations. They are so beautiful that I simply have to share them with you. A pure mathematical and physical elegance. Maxwell's equations are four equations that completely describe all classical behavior of electric and magnetic fields. And I mean everything. Light, radio waves, the electricity in your home, the magnets on your fridge. Everything is described by these four equations. Let me present the simplified version of what they say. Gauss's law for electricity. Electric charges create electric fields that radiate outward from positive charges and inward towards negative charges. Gauss's law for magnetism. There are no isolated magnetic charges. Magnetic field lines always form closed loops. Faraday's law, a changing magnetic field. Ampere-Maxwell's law creates an electric field. An electric current and a changing electric field create a magnetic field. Now, these equations might seem simple when I write them out like that, but their consequences are profound. Let's look at equations 3 and 4 together. A changing magnetic field creates an electric field, and a changing electric field creates a magnetic field. Do you see what's happening here? The fields are creating each other in a cosmic dance. And this is exactly what an electromagnetic wave is. A changing electric field creates a changing magnetic field, and that changing magnetic field in turn creates a changing electric field, and so on. This disturbance propagates through space, and we call this light, or radio waves, or microwaves, or X-rays, depending on the frequency. Maxwell calculated the speed at which these waves should propagate using the constants in his equations, and he obtained the speed of light. And at that moment he realized that light was an electromagnetic wave. This is one of the greatest discoveries in all of physics. Have you ever wondered What transformed our familiar mobile phone into a technological marvel? Let's dissect an icon of our era, the very phone you're holding in your hand. When we truly delve into the world of electricity and electromagnetism, an obvious truth emerges. This mobile phone is in essence nothing short of a miracle. Every time you speak into your phone, that sound instantly transforms into an electrical signal. This electrical signal is then used to modulate, or in other words, ride, on a high-frequency electromagnetic wave, which we call a carrier wave. And then, this carrier wave bursts forth from your device, spreading in all directions at the astonishing speed of light. But the real magic, the part that truly amazes us, lies right here. That wave glides through the air, penetrates solid walls, overcomes even torrential rain, only to find a mobile cell tower many kilometers away. That cell tower, with extraordinary sensitivity, receives this incredibly faint signal. We're talking about tiny fractions of a nanowatt. It amplifies the signal, processes the information, and then transmits it onward. So how is it that all these extraordinary things can operate so seamlessly? How can such a fragile signal avoid being drowned out by the myriad of electromagnetic interferences surrounding us? The answer lies in the sophisticated combination of incredibly clever mathematical techniques and technology. Concepts like frequency division multiplexing, error correction mechanisms, and digital modulation are prime examples. However, the core of everything, the solid foundation for it all, is our profound understanding of Maxwell's equations. And this is precisely where I find the most fascination. James Clerk Maxwell penned these magnificent equations back in the 1860s. Although mobile phones only emerged more than a century later, Maxwell's equations fully described all the physical principles, turning the idea of this phone into a reality. The laws of physics already existed, patiently awaiting technology advanced enough to bring them to life. And this is a powerful testament to the extraordinary power of fundamental physics. Join me in exploring a profound truth. Science isn't just about describing what we see today. It's a journey to unveil immutable principles, eternal laws that will shape the future, opening up technologies our imagination hasn't even touched yet. But here's an interesting fact. Even static electricity isn't as static as its name suggests. I'm going to reveal one of the most common misconceptions we often have. That is static electricity. Remember that feeling when you rub a balloon on your hair and it sticks to the wall? That's when you're creating what we commonly call static electricity. In reality, tiny electrons jump from your hair to the balloon, or vice versa, leaving an excess electrical charge on the balloon's surface. We call it static because the charges appear to be stationary, with no electric current flowing. But this is what makes me think. Even this so-called static electricity still harbors electromagnetic fields that are constantly changing over time. Every time you rub that balloon, you are actually causing those charges to move. And when the balloon clings to the wall, its electric field is at work, polarizing the atoms right on the wall's surface. In other words, it's gently shifting the electrons within those atoms ever so slightly. And all these tiny movements of charge, even if just a little, are creating electromagnetic fields that radiate into the surrounding space. So you see, even the name static electricity doesn't fully capture its dynamic nature. It's just that these changes happen so slowly that we often overlook the electromagnetic radiation effects they produce. However, in extreme situations, such as a lightning strike, static electricity can certainly generate powerful electromagnetic waves. Lightning, in essence, is a colossal static discharge, releasing an enormous burst of electromagnetic waves spanning the entire spectrum, from familiar radio frequencies all the way to X-rays. Now let's explore the connection between the uncertainty principle and electric current. When quantum mechanics comes up, I can't help but share something truly profound about the nature of electric current, tied to Heisenberg's famous uncertainty principle. So what is the uncertainty principle? It states that you can never simultaneously determine both the exact position and momentum of a particle with the absolute precision you desire. If you know a particle's exact position, then information about its direction and speed of movement becomes fuzzy, and the reverse is also true. Let's imagine an electron gliding through a conductor. If we could track every single electron, knowing its exact position and trajectory at every moment, calculating the current would be perfect, without any error. However, a fundamental law of the universe intervenes. The uncertainty principle declares that this is impossible. So how can we discuss electric current when tracking individual electrons is beyond our reach? The answer lies in this. Electric current is not the behavior of a single entity, but a statistical property of the entire system. It is the average flow of charge, calculated from countless electrons over a given period. The quantum details of individual electrons become insignificant. What truly matters is the statistical behavior of a vast ensemble. But prepare yourself, because what comes next is far stranger. Due to the nature of quantum fluctuations, even when no average current flows, small variations in the current still exist. We call this phenomenon quantum shot noise, an inevitable and unavoidable consequence of the quantum nature of charge. In electronic devices requiring extremely high precision, such as components of quantum computers, this quantum noise can indeed become a significant challenge. You cannot eliminate it. This is an inherent, inseparable characteristic of quantum physics. Superconductors, where electric current flows without any resistance. I cannot help but mention superconductors, for they are one of the most wondrous and beautiful phenomena that physics has ever discovered. At extremely low temperatures, certain special materials suddenly lose all of their electrical resistance, and I emphasize all, absolutely zero. You can establish a current in a superconducting loop, and it will flow forever, ceaselessly, without any external energy source. How does this extraordinary phenomenon occur? The explanation lies in the BCS theory of Bardeen, Cooper, and Schrieffer, a true masterpiece of scientific thought. Within a superconductor, electrons are no longer solitary. They pair up, forming Cooper pairs, through interactions mediated by subtle vibrations of the crystal lattice. These pairs then behave like bosons, and the miraculous thing is that they all fall into a single, unique quantum state, a Bose-Einstein condensate. This special condensed state possesses an extraordinary property. It is completely immune to scattering from even the smallest disturbances. It's as if all the electron pairs are moving in a perfectly synchronized dance, and individual obstacles along the way cannot break that collective rhythm. The ultimate result is zero resistance. The current flows freely without any loss of energy. But the marvel doesn't stop there. Inside a superconductor, magnetic fields simply cannot exist. The material actively expels them, as if they were unwelcome intruders. This is the famous Meissner effect, and it also explains the magical sight of a magnet levitating weightlessly above a superconductor's surface. These superconductors are a powerful testament, reminding us that even after more than a century of diligent research into electricity, the universe still holds countless astonishing phenomena waiting to be unveiled. And I am certain that there are many profound things our minds have yet to fully grasp. So what exactly is the true nature of electricity? After that journey of discovery, let's return to the core question. What exactly is electricity, defined precisely? Here's how I define it. Electricity is the dynamic manifestation of electromagnetic fields as they interact with electric charges. It is the ceaseless flow of energy. Through these fields, we witness the coordinated, rhythmic movement of electron quantum waves propagating through crystal lattice structures. It is the powerful propagation of disturbances within these fields, traveling through space at velocities approaching the speed of light. Electricity is not merely the movement of electrons in a wire, though that is just one small piece of the overall picture. Nor is it limited to voltage and current, even though these concepts remain incredibly useful for our understanding. In reality, it's a complex, mesmerizing dance of fields and charges, of waves and particles, where classical and quantum effects intertwine. And the most astonishing thing is that all these phenomena are encapsulated within a single set of equations, Maxwell's equations, supplemented by quantum mechanics, allowing us to comprehend every minute detail at the microscopic level. Electricity is far from as simple as we're often taught in school. It is much richer, more magical, and more beautiful than most people imagine. Perhaps by now you're asking yourself, why is all of this so important? Why should I bother delving into such profound depths? The lights still turn on when I flip the switch, and my phone still charges, right? Why do we need to delve into these complex details? That's a perfectly valid question, but let me share my answer. First and foremost, truly understanding how things work brings a profound sense of satisfaction. It's a hidden beauty, much like the difference between merely looking at a painting and truly understanding the masterful techniques the artist employed, from pigment mixing to intricate composition. I want you to imagine this. You can enjoy a painting without knowing every detail, but I assure you, when you truly delve deep and understand what lies beneath, your appreciation will become infinitely richer and more profound. Secondly, I've realized that when you grasp the fundamental principles of physics, you gain the ability not just to predict, but to create entirely new things. It's brilliant engineers who have created the very phone you're holding in your hand. To develop quantum computers, scientists must deeply understand the quantum mechanics of every single electron. Thirdly, and I believe this is the most crucial point, we must truly comprehend the authentic nature of electricity. This lesson opens up a broader horizon for you. Not everything in this universe is always as it appears on the surface. I've come to realize that the simplified explanations we often learn in school, while useful, are often just incomplete approximations. In reality, I find it's far more complex, more subtle, and often much more fascinating than we ever imagined. I believe that being willing to question every assumption, to dig deeper, and to constantly ask, but how does it really work? That is the essence of scientific thinking. And one final thing about wonder. You know, every time I contemplate electricity, when I truly visualize what's happening the moment I flip a light switch, I can't help but feel an immense sense of awe. I, a tiny creature made of countless atoms, with just a slight movement of my finger, can control the energy fields that fill the entire space around me. I can make energy flow in miraculous ways, lighting up rooms, cooking food, and even connecting me with people on the other side of the globe. And all these extraordinary things, I've realized, stem from the most fundamental properties of the universe. How charges interact, how fields propagate, and the physical laws we've continuously discovered and recorded as equations. Maxwell laid the groundwork with his magnificent equations. Then I, along with Feynman and many other scientists, continued to develop the field of quantum electrodynamics. And now, with just a flick of a switch, your room lights up. I assure you it's not magic. It's far, far greater than that. It is physics. And to me, this truth is more wondrous than any magical tale ever told. So the next time you turn on a light, charge your phone, or use any electrical device, I hope you'll take a moment to reflect on what's truly at work. Imagine the invisible energy fields filling space, the currents of electrons flowing through crystal lattices, and the energy moving through the empty space around the conductor. I believe that electricity is not just what you think it is. It holds a world far, far more wondrous and captivating. You see, this is the alluring, captivating nature of physics. There is always an endless amount of knowledge to acquire, countless mysteries to explore, and profound depths to comprehend. We never reach the ultimate understanding of the universe. Instead, we continuously dive deeper, peeling back layer after layer to reveal an overwhelming beauty and complexity. Instead of viewing electricity as a simple concept you've already understood, see it as a gateway to fundamental principles that govern the entire universe. This is vivid proof that this world always holds strange, extraordinary things and eternal fascination.